Okay, hello. I got another exercise. It's pretty popular in Amazon, questions in Google. So let's get into it. So we got a grid of ones and zeros. So I'm going to display the maximum, the largest square with the ones, right? And as you can see, there are two squares, that 1, 1, 1, 1, and that one. So the area is 4. So we should return 4 here. Okay, and the first idea that probably comes to your mind is that we would want to like iterate through this first square, then the second square, and then the third square, and then the fourth square, and that's the biggest square. And then we're going to iterate through another one. So that square, and that square, and so on and so forth. And that's probably not pretty efficient because we are calculating, like we are duplicating stuff that we have calculated previously. So when we're calculating this gigantic square, let's say that one, then we like repeating the job from calculating that one. And when we're calculating that one, we repeated the job with the calculation of that one. So in that kind of questions, we should probably take a look at the dynamic programming solutions. So when we get that one calculation here of the fourth square, we probably should handle and use that information in the next calculations. Here the idea is that we can just get the previous state, which is going to be marking with our deep dynamic programming array. We're going to be marking which squares are good. Like when the square is good, then we're going to place 2 here because there are two of those are good and 2 of those are good. So we're going to place 2 here, and when there is a good that square is good, that square is good, and that square is good, that would be result of that there will be 2, and there will be 2, and there will also be 2. So there will be square with 2 by 2, 2 by 2, and if we can see that there's all 2's here, then we can proceed with 3 here. Just add the 1. And we're going to be handle that one. I just going to be coding it in a second and show you an example I've prepared. So first of all, we should probably take a look at the edge cases. And when there's an edge case, I should return 0, and then we should initialize our our array, and m is equal to matrix.length, and n is equal to 0.length, m plus 1, and n plus 1. That just for convenience, we want to the first rows to be zeros and the first columns to also be zeros, so that we can handle the previous states as the zero values. So let's go with the first one, m plus 1, I plus plus, and for int j is equal to 0, j is equal to n, and j plus plus. And if now we want to not only process the calculation when we have hit the 1 in the matrix, so because when we're hitting the 0, we should not probably take a look we should not take a look at the squares, because it just doesn't make sense. Okay, matrix, and the matrix of I and j is equal to 1. When this is a 1, then we're going to be dp of I and j, and now we would want to take the minimum value from the surroundings of this value that we're checking. So when we are checking this value, we want to make sure that this value is correct, that this square is correct, that this square is correct, and that square is correct. And we cannot handle it we can say that this is correct. We can only place the value with how big of a square that creates. So if there would be a 2, that would mean that there is a 2 by 2 square, and if there could be a 2, then that means that there's a 2 by 2 square here, and that also goes to that value, right? So when we're calculating that one, we need to have the minimum value from those 3 surroundings, so we have the clear understanding of what are the states of those surrounding squares. So let's calculate that one, and I minus 1 and j with the dp I minus 1, j minus 1, and that would be the minimum. Mat.min, and we need to the last one, I and j minus 1, right? And now we have iterated through all the ones in this array, so we need to keep track of the maximum value. So let's go with the result is equal to 0, and the result is equal to max of dp, the current state of I and j, and the result. And if we have that calculation, we just need to return the result times result. So this result times result means that when we have created a 2x2, there will be 1. When we have also checked that this is a 2x2, there also will be 2, and there will be 2, and there will be 2, and there will be 2x2 squared, there will be 2. And if we have all the 2's here, we can create a 3 here. So we know for sure that surroundings of those squares are also squares with the valid states. So we can place a 3 here. So when there's a 3, we know that everyone around us are 1s, so 3 by 3. Okay, let's run it. And this is it's not working. Okay, where is an issue? Okay, so that we should start with the 1s. And where is the, minus 1 and minus 1, because this array is not prepared for the n plus 1 and n plus 1. Okay. And we should add it to plus 1. Yep, we're super programming, yes, you. Okay, so we got it. So when there is when we have we are doing that one because when we are going to encounter the lowest value from that one, and when those values gonna be 2 in the minimum value from those would be 2. That means that we can safely increment that, and nevertheless we are going to increment that, meaning that when there's a 1, so there's an invalid square right here, and there's an invalid square, then we're going to just adding it to this one and creating a 2. Okay. Let's see that in action. It's pretty quick, and I got an Excel here prepared. Okay, so as you can see, there's this is almost the same example from what we had in LeetCode. There's a 1, and those zeros are not counting. It's just helping zeros. So when I click that and click here, we can see that we have programmed this solution right here in Excel. So the visualization of dynamic programming usually can be visualized in Excel. So that's good. And yep, and as you can see, we will proceed with those 1s and 0s. So we have that one. We have the surroundings are 0 here because we got the 0 element, so there's no square. So they're going to be a 1. So this also we go taking a surrounding, so there's also going to be a 1. But here we got the surroundings 1 1 1. So there are valid squares like 1 by 1 square. And we're going to add a 1 here, so meaning that this is a valid square 2 by 2, as you can see. And also it also applies here, so we're going to minimum, and as you can see, this is invalid. The biggest square you can handle here is 1, and this is not a valid square for 2, and that also comes to here. So we're going to have a minimum from those, so this is also 2. And let's change it. We'll change the 1 here, and you can see we have a 3 here, because the squares have changed. Like this is a 2, this is a 2, and this is a 2, and we have a valid 2 by 2 and also valid 2 by 2 and valid 2 by 2 here. And we're going to have a minimum from those because there's all 3 valids, so we're going to have a 3 here. And that's pretty much it from this video. Like, subscribe if you like it. I'm going to keep up with those videos. Hopefully they're going to be nice.